Hi, welcome to our first video for 6.4 Arithmetic Sequences. The Great Pyramid of Giza, built in honor of the Egyptian pharaoh Khufu, is believed to have taken 100,000 workers about 20 years to build. Over 2.3 million stones with an average mass of approximately 2,300 kilograms each were used. One example of a sequence that can be found in the Great Pyramid of Giza is the number of stones used to build each level of the pyramid. Many sequences have very specific patterns. One such pattern occurs when a constant is added to each term to get the next. This is called an arithmetic sequence. So an arithmetic sequence is a sequence where the difference between consecutive terms is a constant. So an example of this could be like maybe the pattern 1, 3, 5, 7, 9. Okay, and we can see that the difference between consecutive terms is always constant because we're always adding +2 to get the next term. So that is true for any arithmetic sequence. It'll always have a constant difference between consecutive terms. So an arithmetic sequence can be written as A, and then the next term would be A plus D, and the term after that would be A plus 2D. And you might see the pattern here. The next one would be A plus 3D. Okay, you can see that for each consecutive term, we're just adding D to it. So from here to here, we added D, which represents some number, some value, positive or negative. And then we add that same amount again, so now we have 2D, and then 3D. So this will go all the way up until we have A plus D times n minus 1. So this would be like the nth term. Okay, for the nth term, we would have added D n minus 1 amount of times because the first one doesn't get a D, right? So for a sequence that follows this pattern, that arithmetic pattern, A is always going to be the first term. So A represents the first term of the sequence. And D is the common difference. The common difference between consecutive terms. So you can see here this nth term that basically represents any term position in the sequence. Well, we can then rewrite that as a formula, as an explicit formula of the, and it'll be in this form. So any term, so this is the nth term, it's going to be equal to the first term plus n minus 1 times d, because there would be this many times that d would be added to get that term. Okay, so this is a general formula. We're going to highlight it, and we can use it anytime we're working with an arithmetic sequence. Okay, so here's our first example. It says, for each arithmetic sequence, determine the values of the first term, A, and the common difference, D. So for this one here, this is our first term. It's -4. And then the common difference, D. So how much is being added to get the next term each time? So we can tell it's actually just going up by 4. So we can write 4. If you're not sure on how to find the common difference, you can always calculate it by taking one term and subtracting the term just before. So this is the nth term, and this is the term just before that. So for example, we could do T2 minus t1. That's how we could calculate the common difference. So second term in the sequence is 0. So you'd have 0 minus, first term is negative 4, and you can see we get 4. So that will hold true for every consecutive term in the sequence. So there's our answers for A. Okay, let's go for part B. Here we have some fractions, a third, 5/6, 4/3, 11/6. So it's easy. The first term is just 1 over 3. Okay, that's the first term in the sequence. And now the common difference. So we can use our little formula to do that. So we could do the second term minus the first term. We could also have done like third term minus second, or fourth minus third. Those all work. So T2 is 5 over 6. T1 is 1 over 3. Okay, we need to get a common denominator, so we're going to multiply by 2, top and bottom. So we have 5 over 6 minus 2 over 6. Okay, now we have a common denominator. We'll subtract the numerators. 5 minus 2 is 3, so 3/6, which is also a half. So therefore, D equals a half. So this is for part B. And our last term. Here we have the equation. Tn equals 2n plus 3. So what would be the first term? Well, let's calculate it. I'm going to write out the explicit formula first. We'll plug in 1 for n. So that's 2 plus 3, that's 5. So therefore, A equals 5. Okay, we can highlight that. Now, what's the common difference? How much is each term going to go up by? Well, it's actually a little bit easy to see this. It's going to go up by 2, because that's kind of like the slope for this equation, right? As n goes up to 1 and 2 and 3, well, every time it goes up, we're multiplying it by 2, so it's going to go up by a value of 2. So that's obvious just from inspection of the equation. Okay, if you weren't sure, you could always do, I'm going to say or, you could always do D equals T2 minus T1. Okay, we already have T1, it's 5. We could just go ahead and find T2 and then sub that in. So T2, I'm going to write that up here. It would be equal to 2 times 2 plus 3. So 4 plus 3, that's 7. So I'd have 7 minus 5, which is 2. Okay, so we could see how we get the same result for D. Okay, that's it for the first example and the first video for 6.4, and I'll see you guys in the second video.